Yeah, I think there's two part one.
All right. How are y'all doing today? Good weekend? Yeah? It's nice weather, huh?
I thought the thing was due today, so I did it.
Oh, you did it?
And then I read the date, and I was like, man.
Still had time, yeah. Okay, yeah, so that's due on Wednesday, right?
Yeah.
We are going to move on today. Just a reminder, we only have 4 weeks of class left and then final exams. So that means eight meetings. Yep, 8 meetings. We're a little bit behind, but we'll see how things go, okay? All right, so we are going to continue here with Chapter 13, Section 2. We were talking about line integrals, and as a quick reminder, what we were doing was we were taking a surface, and we were just plugging in or restricting the domain to some curve on the ground, taking just those points, plugging them into the surface, and then trying to like drop a curtain down and calculate the area. I think I had a better picture. Where was it? Here we go. Nope. Yeah, this one right here. So some curve on the ground plugged into the surface, and then drop a curtain down, try and find that area. And one of the problems we ran into is we had to find some sort of parametric representation of the curve on the ground. That was kind of a new element to things. Now we'll continue. We did one example of that, or actually 2 examples, I believe. And we are now going to continue by talking about 2 new line integrals. If you remember in the previous formula, we had the line integral over some curve C of the surface, and we had ds here. And ds stood for arc length. So we have 2 new line integrals now. The first one is the line integral along the curve C with respect to x. So what we're doing is we're replacing the ds with dx, and what happens is in the formula it becomes much nicer. Let me take you back to the formula from the other one. Yeah, here's the formula with ds in it. This ds is not a very nice looking thing. What it is the square root of the derivatives of your parametric equations. So you have to take your derivative of your x component, square it, derivative of the y component, square it, add them, square root, and that's what the ds was. But if we define a new line integral just with respect to x, then what we're going to do is just get the x prime, just that dy dt part. So what we're essentially doing is we're taking what was ds, that was the part that was ds in the previous formula. And we are, if we're going to do it with respect to x, then we're essentially saying that that's 0. That this is 0. And so what you wind up getting is the square root of the derivative squared, which is just the derivative of x with respect to t. So that's this right here. And then you could do it with respect to y, which zeroes this one out and leaves this one here. And so visually, what that really means is there's that same picture. We were looking at trying to find the area. Here's our curve on the ground C, right? With respect to arc length, ds, it was the area of this curtain. But if we hold y to be a constant, then the derivative of that is a constant, is 0. Then what we're doing is we're kind of taking this sheet that's hanging and we're projecting it onto the xz plane, and you're going to get this instead. Do y'all see that? It's kind of a projection of it. And so the line integral along C with respect to x is the area under this. And then with respect to y, it's like we cast a shadow of this thing onto the yz plane, and we're finding the area of that. So these are 3 different areas that we would get. Do y'all understand that? Okay. Now, let's see if we can run through an example. Hold on. Yeah. One more thing. You might be asking, why would we want to do this, right? Like, why would you want to go and do a line integral with respect to x or y and not with respect to arc length? Well, it turns out that later on, okay, in a few sections from here, this computation is going to come up right here. This one right here is going to come up a couple of times, a lot actually. And so we'll be doing like the line integral along C of some function of x and y. So this is like some surface, and we're going to want to find that with respect to x, then add it to some other surface with respect to y. When we add these up, we're basically going to do them individually. So this is your line integral with respect to x and then with respect to y. And it'll have some meaning later. For now, let's just make sure we can do it, like we can compute it. So here's our first example of this new concept. We want to find the line integral along C of sine of x with respect to x plus cosine of y with respect to y, where C is the top half of the circle, x squared plus y squared equals 1, from 1, 0 to negative 1, 0, and then the line segment from negative 1, 0 to negative 2, 3. So we'll start like we did last class. Let's try and draw what C looks like, which is the domain. So when I draw C, I have the top half of the unit circle. So something like that. That's 1, that's negative 1. So we're going to go from this point, 1, 0. We're going to move along this curve. We're going to end up here. And then we're not done, right? Then we got to go from the line segment that goes from that point, negative 1, 0, to negative 2, 3. So negative 2, so let's say out here, and 3 up. Let's say is here. Yeah, we'll just put it there, like that. So can you kind of visualize this domain like laying on the ground? And what we're doing is we're going to take every point along this path here, curve C, and we're going to put those into the surface. First, we're going to put all those points in C into sine x, which is some surface. And then what we're going to do is we're going to cast its shadow onto the xz plane and find that area. So we do that. And then we do the same idea with a different surface, cosine y. We plug all those points in, and then we cast the shadow onto the yz plane and find the area of that. And then we're going to add the two together. All right, so that's kind of visually what's happening here. But mechanically, let's see what the mechanics of this look like. Let me get that little box out of here. Okay. So let's take C, and since C is actually made up of two different pieces, let's break C down into C1 and C2, two different paths. So we'll say C1 and C2. So let's try and define these. C1, we've done this already last class. So what we're going to do is come up with some function x, some function of t that's going to give us our x, and some function of t that's going to give us our y. So how do we draw the top half of that circle? We're doing it in parametric though. So cosine t, sine t. And what are our restrictions on t? If we want to draw that half. T is the angle. So we're going to be drawing the circle as we go around 0 to pi. Okay, so that should draw C1, shouldn't it? All right, let's talk about C2. So C2 is a line segment, isn't it? So it's a line segment, it goes from this point to this point. So the way that I would draw this one, oh, let's put the point up here, negative 2, 3. The way I would draw this line segment is by using like a vector equation for a line. So I would start by doing like, I'm going to look at this as like R of t equals R naught plus TV. What's R naught for us?
Any point.
Any point, but we always want it to be the starting point of the line segment, which would be this point written as a vector, right? So negative 1, 0. And then plus t times v, but v is our direction vector, right? So that is the vector connecting our starting point to our ending point. So what is the vector that goes from here to here? You take negative 2, subtract negative 1, so negative 1. And then what's the other part? 3 minus 0. And then if I put this together, I'll put the components together, negative 1 and then the negative 1 times t, so negative 1 minus t. And then 0 added together with 3t, so 3t. This all okay? I mean, we've done this? Okay. So this gives us our component functions where we can get our parametric equations from. So this will be our x of t, and this will be our y of t. So now we can finally write them down. Let's see. X of t is negative 1 minus t, and y of t is just 3t. Do I need anything else? I need something else here. I will need the derivatives, yes. Domain, though, I need a restriction on t. If I don't restrict t, it's going to draw the entire line. I just want to draw that line segment, right? What is it going to be? 0 and 1 always. As long as you do this the way I told you, which is this is your starting point, this is your direction vector that you get by going from the start to the end. As long as you do that, then 0 to 1 will work, right? Because what happens if I plug 0 in here for t? I get negative 1, 0, right? Okay, that's the beginning. And what if I plug in 1 for t? I get negative 2, 3, which is the end. So all the t's between are going to draw the whole thing, okay? All right, so there we go. We've got c broken down into C1, C2, so it's defined. Now let's go and rewrite this line integral. So look at how I'm going to do this. This is going to become two integrals, right? First one is going to be this one, the second one's going to be that one. But each of those two are going to be broken into two because we broke C down into C1, C2. So just watch the way I write this. This is going to become line integral over C1 of sine x dx. Why did I do that? I put C1 up there. I don't know, C1 there. Plus line integral over C2 of sine x dx. And then plus the line integral over C1 of cosine y dy. And then I'm going to erase this. I can remember what that was. And then plus the line integral over C2 of cosine y dy. Y'all understand what I'm saying? Like this is over C, but it's for the first part, and then this one is over all of C, but it's for the second part. Okay, so let's do this guy right here. This first one, I'm looking at C1, which I've erased, right? C1, what were my restrictions on T? 0 to pi, right? Okay, then sine of x means sine of the x is actually the parametric equation we had for x, which was cosine t, wasn't it? So it's sine of cosine t, right? Not sine times, it's sine of x. And then times dx. Dx is the derivative of that x component function, which it was, x was cosine t, right? So the derivative of that is negative sine of t. So negative sine of t dt. We didn't write those down. Maybe I should write them over here just so we can have them. Okay, this was C2. C1 was x of t was cosine t. Y of t was sine t. We never got the derivatives, but the derivative of that's negative sine t, and then derivative of y is cosine t. And then over here, we're going to need them also, right? So the derivative of x here on C2 is just what? Because it's with respect to t, so -1, and then derivative of y with respect to t should just be 3, a constant. Okay. So everyone clear? This was sine of x, and then dx was actually this. These should have dt's at the end of these, sorry. dt. It's okay. I mean, you can leave it just like that. Just remember there's a dt at the end. All right, we good? So could we integrate that if we needed to? Yeah, I think so. This would just be like basic u sub. U would be this, right? The derivative of it's right there. So you would turn into like integral cosine u. And then we could do it, right? We'll get back to it. Let's move to the second integral. Second integral, so I go plus. Now I'm on C2, right? Same function, but I'm on C2, not on C1. So integral is going to go from where to where? 0 to 1 this time, because I'm over here. And my sine of x is going to change, isn't it? Sine of x is now sine of -1 minus t. So sine of -1 minus t. And then times dx, which is the derivative of the x function with respect to t, which is just -1. So I'll put times -1 dt. Okay, that's my second of 4 integrals. So now plus integral. Now I'm back to C1, but I'm doing this one. So C1 went from 0 to pi. And then cosine of what? What's y for us? Sine of t, right? Y is sine of t. And then times dy this time. dy is derivative of the y with respect to t, which is cosine t, dt. That again should be a basic u substitution, right? It should just be, that's u, there's du, cosine u, we integrate that. One more, this one, plus integral 0 to 1, because I'm on C2, and now cosine of y. What's y? 3t, and then times 3 dt. There it is. You feel like you could get those? I think because of time constraints, I don't think I'm going to work through each of these. Basic u sub, this is another basic u sub, basic u sub, basic u sub. Should come out pretty clean. Questions? All right, so that's the mechanics behind it. You got to define what C is first, break it up into different parts if you have to, and then separate this into 2 integrals and make sure you separate those into the different parts of C, and then just go and plug in your different parametric functions and their derivatives, and then you're back to Cal 2, right? It's just definite integrals.
So it doesn't matter which one you set as C1 and C2, right? It's big either one.
What do you mean?
Like, so, well, I guess not, since in the end you're just adding the integrals.
Yeah, you're adding them. Yeah, so it wouldn't matter. All right. Orientation of the path C. So when we're doing a line integral, all right, there's 2 ways that we can traverse the path C. So that's the C that's on the ground, right? We could go, one direction would be going from A to B. The other direction would be the opposite, which would be going from B to A, right? If we call this C, then going the opposite direction is negative C, all right? So the integral over C versus the integral over negative C means what happens if we traverse opposite? Do you think it has an impact on the answer? Think about what this line integral means. If we do it with respect to arc length, right, then we were trying to find, go back to the picture I had. Let me see right here. Okay, if we are trying to go, let's say this is C right here. Okay, that's C right there. And let's say we're going from here moving along like that, and we end up at that endpoint. Okay, so we're going like that. Then the integral is the integral over C of the function evaluated at x and y ds. This ds is the square root of the squares of the derivatives added together, right? So when you take the derivatives, you're going to get something, then you square them, don't you? And then you add them together. That should be a positive number. Regardless of which way you're moving, that should be positive. And then you take the square root. You all kind of get what I'm getting at here? So what we did is we were basically taking this and we were trying to figure out like how wide was each of our rectangles. So the way we did is we approximated it with a little arc length on that curve. That arc length should always be positive. And therefore, if we go backwards, the arc length is still positive. It doesn't matter which way I go. This little length is still the same. Does that make sense? But what if we do it with respect to x? Then what we're doing is we're either moving in this direction or we're moving in the other direction. So if we move in this direction, the width is going to be, you know, like the right endpoint minus the left endpoint. That should be positive in this case. But if we go the other direction, we're going to have the opposite. So our width is actually going to be calculated as negative. Does that kind of make sense? Let's say this is 2, right? Let's say this is 3. So if I take a little width of my rectangle, if I'm moving in this direction, I pick this number here and this number here. Let's call it x2 and x1. x2 is bigger than x1, right? So the width is going to be, you subtract those, that's going to be positive. But if I go the other direction, I'm going to go x1 minus x2, and that's going to be a negative number. And so we can do the same for the other one, but let's just get to the result. Traversal of the path has an impact on our integral. If you're looking at the line integral over C with respect to x, then if you go the opposite direction, it's going to change everything by a sign. So you just get negative. So it's kind of like back in Cal 2, if you go from the integral of some function of one variable, this is equal to the opposite if you switch these limits of integration, b to a. Right? Does that look familiar from Cal 2? You switch the limits of integration, this changes. And this was precisely because we were doing it with respect to x. That's why it changed signs. Same exact thing as here is happening with the line integral. And it also happens if we do it with respect to y. You change the direction of the path, you're going to have to include the opposite sign. But there's no change if you do it with respect to arc length. So if you change the path, you still get the same result. Okay, so that's just something to be aware of. It's a property that we are going to use later on. I'm going to have to prove a theorem to you, and to prove it, I'm going to need some of this. So just remember, I'll be like, remember when I told you about the signs, and sometimes they change. If I change direction, it does, and okay, this is what I'm going to be referring to. All right. So if we change the direction of the path, we may get the same answer if it's with respect to arc length. If it's not, if it's with respect to x or y, the worst that happens is it changes signs, right? We just get the answer opposite sign. But what if we change the path completely, but we still start and end at the same point? Do we get the same answer? So like, let's say I want to go from A to B, and I could choose the path like C right here, or I could choose the path C tilde. Those are different paths. Will I get a different line integral answer? What do you think? Yeah, why? I mean, do you visualize why? No? The curtain's different, right? Think about this. This is getting plugged up into this thing, and then we're dropping a curtain. The curtains are completely different, aren't they? So different paths should give us different answers. I mean, right now it's an open question. Does it change the value of the path integral or line integral? So here's an example to verify what our intuition is. Our intuition is that it should change, right? So here's an example of a line integral where we have two different paths, okay? So let's just call this one C, and let's call this one C tilde. All right? Notice that they both start and end at the same points, right? They both start and end at the same points. But they're completely different paths. One of them is parabolic, the other one is a straight line segment. So let's take a look at each of these paths, and let's define them parametrically. So let's go for C first. So for C, I need to come up with the parametric equations that will draw the curve. So do you remember what I told you last class? If you had something like this, how you could, what you do to come up with the parametrics, if this is like your classic equation from every, like all your classes that you've ever had in the past, y equals some function of x, what I told you to put here? The x will always be t, and then the y will always be that with all the x's replaced with t's. So this would be t squared plus 4t plus 1. These are the parametric equations for that graph. All right? Think about it. All you're doing is you're replacing x with t, right? And replace those with t. And now your y is going to be whatever your t is plugged in, right? To here, here, and here. It has the same effect as this. So what if I change it now and I give you an equation where it solves for x instead of being solved for y? Flip it. Okay, so y of t here should be t, right? And x of t should be 4 minus t squared. Now there is a little bit of an issue here. You still have to come up with restrictions on t. So remember, t is your y coordinate, right? T is your y coordinate. So looking at where we start and where we end, the points we start and end at, you can just look at the y coordinates, right? It's -3 to 2. So we should just go -3 to 2. And let's just check. I mean, this is definitely not a for sure thing, but let's just check what happens. If t is 2, what would we get here? We get 2 for the y, and what would we get for x? 0. And that would be this, right? And if t was -3, we get -3 for the y coordinate, and then for the x, let's see, we plug in -3 here, square it, we get 9. 4 minus 9 is -5, so we're there, right? Understand? Okay, question?
How come on these ones your bounds were constants, but in other situations where where you have to give an actual line or an equation for one of the bounds, why don't you do that here?
You mean like,
Yeah,
like,
so like whenever we're doing
like type 1, type 2 regions and stuff like that?
Yeah, how come that doesn't apply here?
Okay, because in those problems, your domain on the ground was an object that had an area to it, right? Like you were looking at the ground and you were saying, okay, let's talk about, we were trying to define the region between there, right? So we said, okay, the x's are between two constants and the y was between two functions of x. Our domain is not a two-dimensional object anymore like this. Doesn't have area. Our domain on the ground is a curve, C. And so the way we define it is by drawing it parametrically, which means we have a function of x, and x is a function of t and y is a function of t. And so as t varies, you're just drawing dots all over to draw your curve.
Okay.
Does that make sense?
Yeah.
So t will always just be between two constants.
Okay.
Yeah? Okay. All right, so that's C, right? C tilde, let's do C tilde. Do y'all understand that I'm setting up C and C tilde, but when I do the integral, I'm not breaking C into two pieces here, right? Yeah. It's just these are two different paths connecting the same 2 points, so I want to compare them. So here's C tilde, x of t, y of t. Let's see if we can get this one. I can tell you right now t is going to go from 0 to 1 because it's a line segment, right? So let me just do it real quick on the side here. My r of t equals r naught plus tv. So r naught is what? -5, -3, and then plus t times my direction vector, 5, 5, 5, right? And so if I pick off my x part, we get -5 plus 5t, and then we get -3 plus 5t. Questions? We've done this now, I think, 3 or 4 times now. We will need the derivatives, won't we?
Yeah.
May as well get those now. Okay, x prime of t here is -2t. Y prime of t is just 1. Over here, x prime of t is 5, and y prime of t is 5. Okay? All right, now let's do the comparison. So let's do it over c first. Line integral over c of y squared dx plus line integral of c of x dy. So first thing I did was I split up this into 2 line integrals. The first one is with respect to x, the second one is with respect to y. And then now, since I'm over c, I'm going to go from where to where? -3 to 2. And I'm doing y squared. So what's y squared for us here? T squared. And then what's dx for us? -2t, right? dt. So there's your y squared, and then there's your dx, which is this one. And then we need to add to that integral still over c, so -3 to 2, but now we have a different function. It's the x, which is 4 minus t squared, and then dy, what's dy? Just 1, right? That's nice. Okay, so there's that, right? If we compute that, get an answer, that's going to be the area, right, underneath this thing, above this curve, underneath this, underneath these projected on the xz and yz planes. So we've got that area, right? Now we do it for the other one. I'm going to have the computer calculate that for us so we can just check the answers. But let's set the other one up. Over c tilde, we do the same thing. Y squared dx plus over c tilde x dy. So this time we go 0 to 1. And what's y squared now? All that -3 plus 5t. That squared. And then dx was 5 dt. I'll move the other one down here. Plus integral from 0 to 1 again. Now this one. X for us is -5 plus 5t. And then dy, which again is 5 dt. All right, there we go. We should check? Yeah? Why not, right? Okay. All right, let me make this a little bigger for us. All right, first one goes from -3 to 2, and we're doing, what's that, -2t cubed with respect to t, and then we're adding to that another one, which goes from -3 to 2. You could combine these, by the way. You could combine these into one integral now because they're all with respect to t. You could, but I'm doing them separately. Let's see. Oops, no. Whoa, what happened? Four minus t squared. That's it, right? Take that. 245 over 6. Now the other one is you go from 0 to 1. And we're going to get, let's see, negative 5, so 5 times negative 5 plus 5t dt plus, y'all just double check I'm doing that right, typing it in right, 0 to 1. Oh wait, I did the second one first. Okay, that's all right. So 5 times negative 3 plus 5t. All right, dt. That looks right. Oh, I missed squared on both of those? Oh, on that one. Okay, yeah. This one right here is supposed to be squared. There we go. We should not get the same answer. We got negative, right? Where is it? Yeah. Can y'all see the answer here? The path's different. I mean, it could be that you know, along C, maybe my surface was up above, and so when I went along C, that curtain had a positive area. But if I go a different path, maybe the surface is below the XY plane, and so I'm getting negative area. That's what it looks like is happening here. Okay, so the conclusion is that the path matters, right? That's the conclusion. So in general, given 2 points A and B, what happens if we choose 2 different paths? Connecting them, does it change the value of the path integral or line integral? In general, the integral depends on the path. If we change a path, it's likely to change the line integral. There are some conditions which make the value of the line integral independent from the path we choose. We will address that later. Okay, there are some cases where your line integral is path independent. So as long as A and B, right, as long as you're going from A to B, it does not matter what path you take there. You'll get the same line integral every single time. But what's going to dictate that is the function itself, the surface. That's what's going to dictate that. And if that surface qualifies, then we'll say that it's path independent. We'll do it later. But in general, it matters. All right, now we shift gears, okay? Now what we do is, you know how our curve C has been laying on the ground, right? And we've been taking those points, plugging them into a surface and dropping the curtain and finding the area. Now our curve lives in 3-dimensional space, and we're taking those points and plugging them into a function that lives in 4-dimensional space, and you no longer have the idea of dropping the area of a curtain down anymore. But what we're doing is we're adding up all the values. So the way you could say, look at it is, I think temperature, we've done temperature. Let's do mass. Maybe mass might be tough. Imagine, let's go with temperature first. Imagine we take a path through this room, right? Some 3-dimensional path curved through the room. If we wanted to know, let's say we had a function that told us the temperature at every point, right? Then the line integral would be adding up all the temperatures along the path. So you have a temperature at each point, and we're adding them all up, and that's the line integral. Then if you divided by the length of the arc, then you would have like an average temperature along the path. Does that make sense? But how do we add up all the values along the path? That's what this is. Make sense? So we're just going to go from a 2-dimensional curve now into a 3-dimensional curve. That means when you do your parametric equations, you now need not only a function that gives you x and y, but you now need a third piece, a third parametric equation, z. Or you could write it as a vector equation, okay, where you have x of t, y of t, z of t. And so the line integral with respect to arc length again, okay, so now we have line integral over c. C is in 3-dimensional space, so the function that we're plugging into takes in 3 inputs instead of 2. And ds now has a new definition. It's still an arc length, but here's the formula. We've just added that last component out. So do you see how everything's just kind of stretching out into the higher dimension now? All right, now things do get a little weird now, okay, because we're going to change our notation. So let's say that in three-dimensional space, I have some path through three-dimensional space. Going from here, let's say from point A to point B. The way I draw that is by using parametric equations. But we're going to shift now into using a vector equation. What do I use there? X of t? Yeah. X of t, y of t, z of t. So just different notation. I can still draw this curve from A to B using this notation instead of just writing each of these out individually. And our t is still restricted between little a and little b. So if I start plugging in values of t, I start drawing this curve, right? So notice that this formula right here can be rewritten using that notation as follows. First, your integral is going to go from a to b, all right? Which, of course, is our restriction on t, so that's all the same. Look at this notation right here. F of r of t. And I have this big thing in red here to make you aware of what we mean by this notation. This function right here, that's the function, right? F, little f. Our new notation is that. What does f take in here? Look at what is the input of f? You give it an x, a y, and a z, right? An x, y, and z. But this notation makes it look like you're plugging what into it? A vector. Doesn't, I mean, look at r of t, this right there, isn't that a vector? That's a vector. And this function is a scalar function, which means you input into it scalars, right? Some x, some y, some z. But this notation suggests that we're plugging a vector into it. What you need to understand is this notation, what it means, what it represents. It doesn't mean we're really plugging in a vector. What it means is we are going to take the components of this vector function. We're going to take that component, that component, that component, and plug them in for x, y, and z respectively. We're kind of ignoring the fact that it came from a vector, all right? So this is purely notation. The function, the scalar function evaluated at the vector function, weird. But then this, what's this? Well, that's this, right? That's that right there. If I ask you to take the derivative of this, what would the derivative of this be? It would be derivative of that, derivative of that, derivative of that, written as a vector. It would be r prime of t would be x prime of t, y prime of t. When we were learning how to take the derivative of vector functions, it was really nice because the derivative of vector function is just the derivative of each component. So everything was real nice. But then what do? Take the magnitude, right? Take the magnitude. The magnitude of a vector is the square root of the squares, the sum of the squares of each component. So I would basically get this formula, wouldn't I? That's what that is. So this is a kind of a nice condensed notation for that line integral, all right? And in the next part of this section, it'll be even nicer to use that notation. All right, let's move on. Just as you would suspect with what we just did at starting class, you can have a line integral over C with respect to arc length. But now we have three other possibilities. We can do it with respect to x, or we can do it with respect to y, or we can do it with respect to z, or with respect to arc length. So now there's four possibilities here total, right? Arc length, x, y, and z. I can't show you a visual of what we're doing because, again, we're in four-dimensional space with this thing. So can't show you like a shadow being cast or anything like that. It's just not possible. Just had that panic that I'm not recording. I'm okay. All right. All right, and again, just like we said before, these integrals are going to show up together. So look at this notation. There's one line integral over C, and then you have some p function of x, y, and z dx plus some q function of x, y, z dy plus some r function of x, y, z dz. What this really means is just you do them individually. Okay, you just do them. But the notation is to only write the integral once. Integral sign once really means the integral on each of those three things. All right? Have y'all looked at the notes online for the formulas for Chapter 13 that you're allowed to have on the final? Have you all had a chance to look at those? You look like you're, do you have them? Did you like print them out at the beginning of the semester?
Yeah, there's some of these.
Yeah, hold on. How many pages? Yeah, can you take those out?
Like 11.
Can you take those out real quick? Yeah, let's go back there further. These are the formulas that I allow you to have. These are front and back. These are just the formulas for Chapter 13. Just Chapter 13. There's so much stuff here. Yeah, I don't expect for you to memorize those because it's just way too much. So, you know, there's a lot of stuff in here in terms of formulas. So if it feels like, oh, it's overwhelming, it is. Just, I would print that out and start using that when you're doing your work because you want to be able to reference it during the final and it not be like the first time you've ever looked at it, you know? You want to know where the formulas are. Okay, so here's our first example of this new line integral where we have our curve in three-dimensional space. So find the line integral over C of this thing, where C consists of the line segments, plural, 2 segments, from 0, 0, 0 to 1, 2, negative 1, and from 1, 2, negative 1 to 3, 2, 0. I think for the sake of time, let's just do one of the 2 line segments, all right? But you do need to understand that this would have to be broken up. This would be C1, and then this would be C2. Do you all understand? Right? So this line integral is going to break into 3 pieces, right? 3 different integrals. And then each of those would have to break up into 2, one for C1 and one for C2. That would take a little while, right? Okay. You know, maybe what I'll do is let's come up with the parametric representations of each of these C1 and C2s. So C1, watch how I do this. I'm going to write it in a vector form instead of x of t, y of t, z of t. So what is the vector form of this right here? So how do I draw that line segment? This one's kind of easy. That's why I'm just going straight to it. 2t, t, 2t, and negative t. So that was, again, because it's a line, you're starting here, so your initial r naught is 0, 0, 0, and then plus t times v. Your direction vector is just that vector, because when you subtract, you get that. And so it just goes straight to that, right? Now, I'm going to need the magnitude of this. Sorry, the magnitude of the derivative, right? In the formula, I need the magnitude of the derivative. Oh, wait, hold on. Sorry, we're doing it with respect to x, y, and z. I apologize. I thought we were doing with respect to arc length. So we don't need that. We actually need each of the pieces. So let's just take the derivative. Let's not take its magnitude. The derivative of this would be 1 to negative 1, right? All right. And what's t between? 0 and 1, right? Okay. And then we would have to do the same thing for this one, right? Break that one up, get our vector equation, take its derivative. T would go from 0 to 1. So let's start doing this. That becomes line integral over c of x squared dx plus line integral over c of y squared dy plus line integral over c of z squared dz, which then in turn would become line integral over c1 of x squared dx plus line integral over c2 of x squared dx plus line integral over c1 of y squared dy plus line integral over c2 of y squared dy plus line integral over c1 of z squared dz plus line integral over c2 of z squared dz. And like I said, I am not going to do these just for the sake of time, but you understand you would have to do the same thing we did here, right? Break it up, or are y'all okay with that? You sure? I'm just skipping that. You sure? Okay. All right, so let's do this first one right here. This one right here would become integral from 0 to 1 of what's x squared? Is t squared, right? Because I'm picking off the x component here. So t squared, and then what's dx? It's this piece right there, right? That's dx, so that's 1. So that's just 1 dt. And then plus whatever that one is, right? I'm skipping. Plus integral from 0 to 1. Now y squared dy. So what's y squared? 4t squared. And then dy? 2, right? So 2, you can put the times 2 dt there. There we go. And then I'm skipping that one, so that would go here. And then plus integral from 0 to 1 again, z squared. So it's going to be t squared. And then dz is -1, so -1 dt. And then we have this one here. And look, these integrals are pretty straightforward, aren't they? These are just little power rules on those. And all right. Any questions? Because I'm going to move on.
So those two lines are just two lines that are somewhere in three-dimensional space, right?
Yeah, like the first one, C1, goes from the origin to some point, and then that second piece goes from that point to some other point. So this is like C1 and C2. C is all of it together.
Oh, okay.
Right? Does that make sense?
Yeah.
So it's like if this were somehow, well, it's not the temperature, but it could be, then we're just like kind of adding up the values all along this thing. It's a little different when you do it with respect to x, y, and z, but
So this still breaking down that we just did with the reintegral, that's just that first line, 2-1.
say that again?
And how it was like 1 and 2.
Uh-huh.
The ones that you just did, that was just C1.
That's right. That was only this to here.
Breaking it.
So I'm skipping this part, but you would need to do that. So you just come up with a new R2 of t for this one. And then take the derivative and plug in the same way we did here. Okay. And moving along. Again, we shift gears. Now we shift gears significantly. We're now going to do something called line integrals over vector fields. Now, this is probably the most important part of this section right here. So recall back from 10.3 the way we define work. So this is like physics. Work is defined to be a force vector dotted, that's dot product, dotted with the displacement vector. So this was the picture that we had back from 10.3 is if you give me a force vector, right, and you give me a displacement vector, then to compute the work done, you dot this vector with that vector. So what happens if our force vector is perpendicular? You have 0 work. Did I go past it? Where is it? What? You know what? That's something ain't right there, huh? We should get negative, right? I wouldn't trust that number now. I don't trust it. Right? Because two vectors are orthogonal what? If their dot product is 0? So what the hell am I calculating there? I'm curious now. Hold on. Dot product of PQ.
Maybe you're not exactly at 90 degrees.
Yeah, but I wasn't even getting close to 0, was I? Look. Like, see, it's... Whoa. See, I should be getting close to 0 here, and then it should be going negative. Something ain't right. Maybe it's the way I have P and Q defined. My point... Okay, let's not get into it right now. I can spend 20 minutes in there trying to figure out what's wrong with that. Okay, so now, imagine a point moving along a curve C. We're going to be in two-dimensional space right now. Imagine a point moving along a curve C within a vector field. So remember, we started this chapter with vector fields. Vector field was at every point there was this vector, right? Could be magnetic, could be, you know, what were the examples I gave? Magnetic, gravity, right? So imagine at every point there's some vector. And that vector, that vector field we have is applying a force to the particle moving along the curve C. Then the total work done by the field, by the vector field, is the sum of the work done at each point. So I'm going to show you this visually. Okay, so what we have here is a curve. The blue is a curve, right? So what we're going to be trying to do is move along this curve. This right here, do you remember that thing right there? Do you remember that thing being our vector field? Yeah. And we were doing examples and we'd plug in a point and we say, hey, what is our vector going to do? So remember, there is a vector field here, all right, at every point. And so what we're doing is we're saying if we are going to move on this curve, where's that one? This one? If we are going to move along this curve, then at every point along this curve, there is a vector from the field. So let me try and move this one up to that point so we can see that they match up. See what I'm saying? Like that red vector is the representation of the vector out of the vector field. Okay? If we take that, let me take that out of here. If we take that, and as we're moving, right, we have displacement, don't we? We have a displacement. As we move, we're moving, right? So that's our displacement vector. And the way we get that is to, well, what's the green vector and what's this little shorter purple vector? It's hard to see, it's purple, but what do you think that purple vector is and what do you think that green one is? Pardon? Okay, the green one is the unit tangent vector, and the purple one is just the tangent vector. So remember, if you move along a curve, we could find a tangent vector by just taking the derivative of the vector function. So the purple one we can calculate pretty easily. Let me move this thing along. So as I move through here, the purple one and the green one point in the same direction. The only difference is that the green one always has a length of 1. And that's the one we're interested in because what we want to imagine doing is, let's just say I moved just from here like infinitesimally to there, right? Just a little infinitesimal movement. Then what I could do is say, well, the work done would be that vector from the field at that point. Let's say right there. It would be the vector from that field dotted with this little displacement vector, right? And the way I get this displacement vector is to take the unit tangent vector and scale it back and make it like infinitesimally short. Does that make sense? So look at what that calculation looks like algebraically.